Okay, hello everybody. Uncanny. I'm talking about NeRFs and robotics. Amazingly good timing. Well done. Thanks, John, for the incredible talk, and well done, Mark and Dorsa, for the excellent organization of speaking order here. So I'm hoping to address some of the questions that were just coming up in the Q&A about how might we use NeRFs in robotics, how might we overcome the challenge of real-time training and speed, and so on. So I'm Max Schwager. I run the Multi-Robot Systems Lab here at Stanford, and I've been really fascinated with NeRFs and how we can integrate them into the robot autonomy stack, and what do they offer us in robotics. So one of the first things that we've done that I'd really like to share with you guys is something called NeRF Bridge, which is basically a NeRF bridge, so a software tool that allows you to integrate real-time NeRF training within a larger ROS ecosystem for autonomy. This is largely the work of my PhD student Javier, whose picture is up there, and he's got a poster here as well. So I'll just show you this working in practice. So this is our lab where we do a lot of drone research. And we have the first-person camera view of the drone here. We have the drone flying here from a third-person view, and here's the state of the NeRF as it's being trained. So this is all this is all ROS wrappers, basically. So it's really a software tool to make NeRFs more accessible and easier to use for roboticists. We're really building on top of NeRF Studio, which is a really full-featured, beautiful, open-source NeRF training package from Anju's lab at Berkeley. Okay, so you can see that you get the NeRF model in real time. This is all just a screen capture, right? So as you see, that's the real-time training of the NeRF. And part of the secret here is acquiring the camera poses to pair with the images for NeRF training. This is something that John alluded to, and I'll get back to that in a minute. One thing that's really great about NeRFs is, right, as your robot is going around collecting the imagery to train the NeRFs, you can interrogate the NeRF from a virtual free-flying camera. So you can imagine in search and rescue or other situations, you might want a human operator to go interrogate the model to find out where human survivors are, to find out where dangers might be, whatever. And that can happen in a totally asynchronous way as the robot is collecting data. So you have a virtual camera, a real camera, and they can be in totally different places, which is pretty cool. So that's what we're showing here, a virtual camera flying around. And this also works outdoors, and this exposes some of the guts of what happens inside NeRF Bridge. So we're basically pairing the NeRF training with a front end, a SLAM front end that gives us the camera poses in real time to hand over to the NeRF training. And here's OrbSlam 3 running in sync with the NeRF as we're training this facade of a building, and this is all flying outdoors over Lake Log, which is a lake here on campus. Okay, so getting into the details a little bit, what really is NeRF Bridge? Well, we take the image stream from the robot, and then we put that into a SLAM node, which is totally modular. We use OrbSlam 3. You could use whatever SLAM or VIO package you like. And that spits out the camera poses in real time, and then you pair those with the images, and that goes into the data loader for NeRF Studio. And so you have this dynamic data stream that's constantly being operated on by gradient descent within NeRF Studio, so you get this dynamically updating NeRF. Okay. Great. So now we can train NeRFs in real time on board the robot as it moves around. There are a number of questions that this motivates and that we're working on. So how can you navigate a robot safely without hitting things as it's training the NeRF? How can you do active view planning? How can you send the robot intentionally to go grab certain views that you expect will improve the NeRF? How can you integrate this with a human language interface? So now we have all this rich visual information in the scene. Can we tell the robot, hey, go fly around that fountain? And the robot can understand what a fountain is, maybe using large language models, and then ground the notion of the fountain in the 3D scene using the NeRF or something related to the NeRF, and then execute a motion to fly around the fountain. And then finally, can we scale this from multiple devices, multiple robots, streaming images simultaneously? You might have a group of drones, ground robots, you might have wearable devices on humans or phones, autonomous cars. Can all these streaming data sources be integrated through a communication network to train a single NeRF? So we're working on all these problems. I'm going to very quickly give you a sample about how we're attacking safe navigation for a robot in a NeRF world. And this is primarily work by my student Tim Chen. So the idea that grounds this whole research is to interpret the density field of the NeRF as belonging to a Poisson point process. And this is all motivated by the underlying volumetric rendering process that John Barron talked about. So it turns out that if you make this interpretation of the density field as leading to a Poisson point process, there's a lot of math that goes behind this, but at the end of the day, you can compute hard probabilities of collision for a robot body. So knowing that I position my robot in this location in the NeRF, I can spit out, oh, the probability of collision is 0.01. And then I can build a map, an occupancy map from the NeRF and from the probability of collision. It has the interpretation that if my robot is in the free space in this occupancy grid, then I'm guaranteed that I won't be colliding with that specified collision probability. And then we can solve a chance-constrained planning problem. For example, we can plan with A star an initial trajectory, and then we can build safe corridors around that initial trajectory, and then we can spline a dynamically feasible trajectory for the robot to fly in to respecting the collision constraints through the map. And that's what these trajectories look like. And then we can execute these trajectories on board the robot. And this whole building the safe map and then planning trajectories, it can be done at 10 hertz. It's very fast. So this can be replanned online as we're training the NeRF model online. And now we have the potential to have a fully integrated real-time NeRF autonomy stack where we're training the NeRF and navigating safely with respect to the NeRF. Okay, so thanks to Javier and Tim for this really cool research, and I'm happy to share that with you, and I'm glad to take any questions now. Thank you.
Do you have any questions? And Jitendra, you can come on up. So I can ask a question, if I may. Do you interpret the opacity from the NeRF as the solidness in terms of the collision, or how do you map that?
Yeah, so the opacity is basically represented by that density field, and it's been kind of well known in an intuitive sense that the density field had something to do with the differential probability of occupancy, and basically our work just formalizes that and really ties it tightly to the volumetric rendering, which also has something to do with the differential probability of occupancy. It's actually the probability of opacity, so we're kind of conflating opacity and occupancy, which is often valid, sometimes not. It won't work for windows, for example, or mirrors. We're working on it.
So, thank you very much, Mac. And then next up we have Jitendra from UC Berkeley.
Hello. So normally when I come here, I usually show photos of and videos of walking robots, but today I'm going to talk about manipulation. But it's in the same philosophy. We developed this framework called Rapid Motor Adaptation, or RMA for short, which we used to train in simulation and then apply that policy in the real world. So here, we did this for rotation by a multi-fingered hand, and we had a paper on this last year. So let me show you some demos of that. So this is a multi-fingered hand, an Allegro hand, as you can see, and it's rotating various objects. And you should be able to see that these have a variety of shapes and weights and so on and so forth. And, okay, more examples. And we picked on this problem as a canonical dexterous manipulation problem. And here is the surprise. This is being done with only proprioception as the sensory signal. There is no vision, there is no touch. And this to me was a surprise that you could do this, right? Okay, but it turns out there is a subtlety. It depends on the various kinds of hand rotation problems are not equally easy or equally difficult. If you have the object in the palm, it's a much easier problem because it's being held up there. Even this, when the object is at the top and you are rotating in the z-axis, it's not as hard a problem because basically you keep on moving it fast enough so it doesn't fall down. Where you get into difficulty is if you want to rotate about an arbitrary axis. And when we did this, this is going to be presented at this choral, what we found, which was very satisfying to me as a former or current vision person, is that vision is absolutely necessary. And not just vision, but touch is absolutely necessary. And this, I believe, I do not think we are going to get dexterous manipulation without the use of vision and without the use of tactile. So let's show you what we are trying to do. So we want rotation about an arbitrary axis, so your canonical ijk axis, or in fact any arbitrary direction. And you want continuous rotation. So that's the challenge. So how do we do this? And first, let me prove to you that we can do it. So here, what you should see in different rows, one row corresponds to rotating different objects about a particular axis. So in the top row, it's the x-axis. So let's see if there's demos. So different objects are being rotated in the top row about the x-axis, then it's the y-axis, and then the third row is the z-axis. That's what we had shown earlier. And hopefully you see that it works. And the question is, how does it work? It turns out that we can do it, and we follow the same paradigm. You train in simulation, and then you carry over to the real world. And you need vision. You have this RGBD camera that is looking at the objects. You use all the vision tricks now. We have good sort of off-the-shelf segmentation with something called SAM, segment anything. We have tactile sensing. So each of these 4 fingers has got a digit sensor. If you've heard of gel sight and digit, and then there is some later version of that which will become public soon. And those tactile images are shown there. So all of this is needed. What we do is we train a policy in simulation. In simulation, you try to learn to rotate the object about any particular axis, and you have access to the shape. So it's privileged information. This is a paradigm that has worked very well. So in simulation, you're trying to rotate an object, and then you know the shape of the object. And then the system is trained with that. And you train with many, many different shapes, and all those shapes are known. So that's what I have this as this object mesh. What we do is that we take them, compress them into this Z sub t. So this Z sub t is what is really needed. You do not need the absolutely detailed shape of an object to rotate it. You need some compressed version, but not just the shape, also like friction and various other properties. They are all captured in Z. And then we have this control policy which has been trained with reinforcement learning. Of course, this works in simulation. Okay, then how do you make it work in the real world? In the real world, you will not have access to the true shape of the object. What you will have access to is a computer vision looking at the object, and you see just the front of the object, and you will have the signal from the tactile from each of the 4 fingers. And those observations are shown here at the bottom. There's O sub t's, and these go into a transformer, and then the transformer tries to predict the z, and this is a supervised learning problem, and then after that it goes into the control policy. It's the same RMA philosophy which we use for legged locomotion. And it works, and well, the proof is what you saw earlier, but we can be very quantitative. But what is really satisfying to me here is that on the left, you have, let's start with the extreme right. That's when the rotation policy has access to the shape, full shape. That's the oracle solution. Okay, that's the best what you expect. When you go to the extreme left, that's what you get when you don't know anything, and it's poor. And in between, you have the first 2 cases are just vision or just touch, but when you use vision and touch, you get as good as the oracle policy. So this is the grand result, which I'm very happy with, and we validated that in many different ways. Thank you very much.
Thank you. Thank you, Jitendra. Any questions from the audience? Monroe, thank you. It seems like this privileged learning, and we've done some work together, is very powerful. Is there some natural sort of bottleneck there? I mean, it strikes me that one thing is if it's hard to make the privileged data to begin with, how do I deal with these kinds of situations? Or do you think that that's a misunderstanding?
I think any setting where you have a good simulation environment, I think that's the bottleneck. Sometimes it might be easier to work with the real world than by creating a simulation environment. But if I had the kinds of tasks that have been achieved in this paradigm, in my view, are much more impressive. There is this drone racing thing. There was a paper in Nature from Davide Scaramuzza's group. you get performance better than humans, right? When you do it by sort of a human does some demonstrations and then you copy them, the best you can do is the human. This way, when you do reinforcement learning and simulation, you can do better than humans at the cost of course, of needing a simulator. So wherever you can create a simulation environment, I think this is the way to go. So I'm...
Perfect. Thank you, Jitendra. Monroe is up next from Stanford, and I think there was a question. Perhaps you can take it offline. Thank you.
All right, thank you very much. Can you hear me? All right, fantastic. So today I'm going to talk to you about our work in DenseTact. So I direct the Assistive Robotics and Manipulation Lab here at Stanford, and we look at how we can build effective collaborative robots. A big piece of this, as you've been hearing in this session, is we need robots that are capable of touching and manipulating the world comparable to the way humans can. So my lab has been focused in one of our initiatives in building these types of sensors we call DenseTact, and today I'm going to highlight quickly a few of our works in this space. So to kind of start off here and kind of set the stage, if you look at a lot of the existing consumer robots, they're very capable of visualizing the world, moving around the world, but touching the world is very difficult. If you're willing to pay a little bit more money, you can have these industrial systems that are capable of manipulating, but often the traditional manipulators are manipulating pretty large objects, and the dexterous things are very complex, and if something is soft, you have to be very mindful. In the space of handling kind of soft objects and making sure you have good grasp stability, there's great advances in soft robots that can actually conform and wrap around objects that you might want to manipulate. So a question you might want to ask yourself is, when does tactile sensing really make a difference? And I would argue that it does when there's key information in that point of contact that can't be detected through vision or proprioception. And so just some examples here might be object softness, or perhaps if you're reaching into this bowl and I say, find a particular screw of a particular type, if they all look the same and they're relatively the same, this might be kind of hard to do if you don't have tactile information. If we look at how humans are able to manipulate their world, we see that human hands are soft, they can sense objects' shapes, and they have the ability to feel forces and stresses when you touch something. So the holy grail, I would argue, for a robotic fingertip is it should be high resolution, have high sensitivity, be reliable, easy to use, compact, and inexpensive. And once you have that kind of system, you can imagine it being able to do things like detect slip for objects that it's holding, be able to manipulate very small objects. Imagine pushing, assembling this sort of microchip board here, manipulating very soft objects as well as doing very articulate hand objects with robustness and stability. So this leads us to our work in DenseTact. So there's a lot of work in this space. You'll see many sensors that have these principles. Effectively, with all these types of work, you have this elastomer gel, some LEDs that are illuminating the interior. There's a camera, a sensor surface that's interacting with the environment, and then a housing that holds the whole system together. So this is our DenseTact 2.0 version. So this consists of a camera, internal LEDs, a very, very soft elastomer gel. If you want to see it, come find me after. I have a little demo piece to show you. And a reflective exterior where we watch just the boundary of contact. And so this is an exploded view of that design. We iterated on that design recently, and we shrunk it down to something we call DenseTact Mini. It gives you another option depending on what types of tasks you want, but we brought the cost down, I'll show you in a minute, and added this sort of fingernail ability for certain tasks. And so the cost for just the sensor itself, if you want the larger one, it's about $80. If you just want the smaller one, it's under $30 to construct, and it has really good resolution. So how does it work? So if you have an LED, the LED bounces off the surface, goes into the camera. Depending on how the surface is rotated, you have a change in light intensity, which allows you to estimate a surface normal. If I give you a bunch of surface normals in a boundary condition, you can use those with Poisson integration to give you back your surface. But this is a very complex thing to do and can be hard if there's noise in the intensities you measure. And so actually retrieving this is quite complicated. Our approach was to actually use a neural network to perform that Poisson integration for us. Additionally, if you want to see forces, you need markers on the surface. If you imagine something under pure shear, you need to watch those markers to understand, and the surface normal wouldn't be enough in pure shear. So we generated continuous patterns that allow us to have a very soft medium that when it's extremely deformed, you can still track that force over extreme deformation. So here is our DenseTact 2.0 being trained for forces. Image comes in, and the wrench you see on the right is coming from this ATI sensor, which we're able to show in our paper, we're able to learn. And so this is the architecture that shows you can bring in the deflected image, the original image, and then reconstruct through regression the shape per pixel as well as the forces, the net wrench on the sensor. Quickly showing you some applications in this space. We were able to do some really cool things in screw manipulation. So we can say, can we look into a bowl of screws? Can we do geometric manipulation to actually pick a screw in our hand, recognize what we're holding, and then sort it into a target container? And then we were able to have really great performance with that. And then on the other side, we say, can we actually manipulate things off of small tables? So if you look at how people manipulate things, you can see someone using a fingernail to pick up a coin and pressing into this, using adhesion forces to pick up this small system. We're able to replicate these types of results here with our DenseTact Mini. So you can see us picking up the coin off of the table. We can do this quite reliably, as well as instances where we can pick up items by pushing into surfaces. And then I'll finish here just showing you some of the performance results for these. We actually have really good success rates for this system with the different types of grasping. And then these are all of my amazing students, some which graduated. Thank you very much.
Thank you, Monroe. Any questions? Ken, go ahead.
Monroe, it's really interesting work because I've always said one of the things that robots can't pick up is like a paper clip, for example. So when you're getting to be able to lift those seeds, are you using some kind of adhesion onto the surface? Is that what's going on?
So because the items are so small and the gel is so soft, that when we push it in, we think there's a combination of like the electrostatic as well as van der Waals forces that are acting. And just like you saw with that quick primer video with the person, we get very reliable adhesion, and then we use the fingernail to scrape it off. Yeah.
Oh, great idea.
Thank you very much, Monroe. Up next, over here in Chelsea.
Awesome. So today I'm going to talk about data. I'm really interested in this problem of how we might allow robots to generalize to real-world situations. And I think that in machine learning with, for example, generative AI, we've seen a really successful recipe where we combine large expressive models with broad data sets and get models that actually work in a variety of circumstances in the real world. And if we wanted to try to replicate this recipe for robotics, I think really the big challenging part is how we might get the data. I think we know how to train the models. And I think that part of the challenge here is that in robotic learning, typically researchers will collect a data set for the project, do their research with that data set, and then start a new project, not use any of the data from the previous project, and collect a new data set, and so on and so forth. And do this for every single project. And in contrast, if you look at what machine learning research does, it's a lot less wasteful with data. Typically, a data set is curated once, such as ImageNet, and it's reused many different times. Or even better, researchers might be reusing a pre-trained model downloaded from the internet and not even actually even having to touch the data set. So I'm interested in how we might allow robot learning to look a little bit more like the right. And if we didn't have to recollect ImageNet for every project, then we might be able to make a lot more progress. Specifically, if we're able to try to share data and pre-trained models across institutions. And so to think about this, I'd like to think about what's stopping us from actually trying to share data across institutions. And I think a big part of the challenge is that a lot of the existing data sets we have are kind of like islands in a giant ocean, where each data set is representative of a small part of the possible situations that a robot might encounter and a possible set of sensors and so on and so forth. And so each of these might be a different existing data set, but inevitably, the next experiment we might want to run might not be well covered by the data that has been collected previously. And furthermore, each of these data sets are in different formats in different places, and it's hard to actually combine them and leverage them all in a single project. So I'd like to talk about two efforts. The first effort is whether we could actually potentially try to make a larger island and do so in a way that is using design choices that the community has agreed upon, such that we can actually try to gravitate towards that island and try to see what we can do with a broader data set and a broader island. And to do this, we've actually reached out to a number of different people and actually been really surprised that a lot of people are eager to contribute. We have a Slack channel with 70 people and 18 organizations. This is an ongoing effort, but so far we've collected more than 30,000 demonstrations and more than 600 scenes, and you can see some examples of the data on the right. And many of the people that have contributed to this community-driven effort are in this room. And beyond that, we've also been interested in whether we can also just use the data that we already have. And to do this, we just need to put all the data in a common format and then train a model on the data. It seems fairly simple, but in reality, no one really wants to just do all the effort manually of putting all the data in a common format. And so the idea here was maybe we can do this as a community. And Quan Vuong at Google reached out to a bunch of people asking if they'd be interested in contributing to this effort. And it turns out that a lot of people were eager, 174 people at least so far, were eager to put their data in a common format. And this led to an aggregated cross-embodiment data set that has more than 1 million demonstrations across 22 embodiments, collected by 34 different research labs and 300 different scenes. It's really easy to download and use this data set. It's just with a few lines of Python code. And we can also train models on this data set. So we reused some architectures from previous work, specifically the RT1 and RT2 architectures. These models take as input an image and a text instruction and output the discretized end effector actions. This is just trained with supervised imitation learning in a very simple way. And RT2X is actually using a pre-trained vision language model in order to get additional leverage from web data. One thing I'd like to emphasize here is, in this case, in these experiments, the model is trained in one lab and then evaluated in other labs outside of the control of the person who trained the model. This involves sending checkpoints over the internet, and with the larger model actually querying actions over the internet to run on the robot. Experimentally, we see that the model that was trained on the cross-embodiment data actually, in most cases, outperforms the original model that was designed for that data set, as well as the same architecture trained only on a single embodiment. And so this means that training on cross-embodiment is improving training over in-distribution data, including the original method from the lab. And we see on average a more than 20% absolute performance improvement in success rate. We also see that if we evaluate the robot on its ability to perform instructions that were not even represented in the data set for that robot, but were represented on data sets from other robot embodiments, such as moving an object between two other objects, the robot is able to successfully accomplish this task by nature of training on data across all of these different platforms. And we see an improvement in success rate that's very drastic for these kinds of held out instructions. So really the takeaway here is I think that we're at a pretty exciting point in robotic manipulation where large-scale data is starting to become a reality for learning low-level motor control. And there's also lots of opportunity for really expanding this data set in the future and having other people contribute data. I think that ideally this wouldn't just be a robotic manipulation effort. Really any kinds of robotic data could be put into this data set. And I should also mention that I'm talking about this myself, but this was a really massive effort, and really kudos to Quan, who is leading it at Google, Carl, who did a lot of data wrangling, who's a postdoc at Berkeley and Stanford, and also a really large number of other people. Great, happy to take questions.
Howdy. Okay, thanks for the talk. So at the start, you sort of said that, like, you know how to train these models. Do we? Like, what sort of, so suppose that you did have this like massive, really well-structured data set from potentially, as you said, a bunch of different robot types as well. So not just manipulation, but also quad rotors, self-driving cars, dogs, whatever, right? Like, do you have any sense of what sort of objectives that we would need? Yeah. Similar to how people use like language modeling for NLP.
Yeah, that's a really awesome question. I think that we don't fully know how to train these models, and so I was bluffing a little bit there. I think we have it figured out much more than the dataset side of things, and so I think we're way further behind on the dataset. But in terms of actually training these models, I do think that we have some hints. So I think that imitation learning has gotten us far. I don't think it'll get us all the way, but it's a very powerful tool. And then also more self-supervised objectives like goal-conditioned imitation learning, goal-conditioned reinforcement learning, perhaps even generative models that generate future goals or generate video are all very are candidate objectives that I think are pretty promising.
All right. Thank you for the answer.
All right, thank you, Tommy. Before I let you speak, I want to encourage those of you standing at the back, if you'd like to have a seat, there's plenty of seats up here, so feel free to come up. Of course, maybe the light is better there, so that's fine. Our next speaker is Professor Tomizuka from Berkeley.
Thank you. So, I'm Masayoshi Tomizuka. I'm from Mechanical Engineering Department of UC Berkeley. And I'll be talking about industrial robot in contact with object and environment. So there are so many robots now in use, and there may be something I hear 3 million industrial robots in use across the globe. But not only quantity, but the industrial robots are required to be more intelligent, and some application like flexible automation or bring robot out of the cage and let human and robot collaborate. So they need lots of intelligence. And so my lab has been working on this type of intelligent robot for many years, and such as motion planning, assembly, contact manipulation, and so on. And focus of my talk today is industrial robot in contact with object and environment. The application appears in assembly, grasping, manipulation. Jitendra was talking about something. Apparently, I think we have done something very similar to what Jitendra has done, but it's not really based on the human demonstration. So we cannot go beyond human. And then the emphasis is on effective learning, stability, robustness, generalizability, and so forth. So the first work I would like to introduce is Shuran and his company on efficient sim-to-real transfer of contact-rich manipulation skills with online admittance learning. And what we do want to hear is something like contact-rich manipulation. We have 4 example videos shown here. And in doing this, we have to first bring robot, make physical contact and engage with environment, and then robot manipulate object by applying suitable contact force. But in doing this, what normal traditional way of making this happen is by human experts. Human experts do more the programming, robot more programming. But that's not efficient. And I think in recent years, we hear that lots of good things achieved by learning method, the reinforcement learning. Now, but if we do learning with actual robot, it may be time consuming, or even during the learning, everything may break apart, hitting the object, floor, and so forth. So it's not necessarily the best, but on the other hand, if we try to do learning just by simulation, we may have to overcome the problem of sim-to-real gap. And to overcome these problems, we introduce some framework, 2-stage. First, we go by offline phase. And here you utilize model-free reinforcement learning to learn the skill. Skill include how we move and what kind of control parameters, admittance control parameter we set. And to make robustness, we include some domain randomization. And this is the first phase. Then we go to the online phase and utilize the output of the force-torque sensor to update admittance control parameter to optimize robot motion. So we have some feedback from the real operations via the force-torque sensor. And optimization objective is to make the robot motion smooth and tracking performance good. And so this is the way we have been doing. And here we have some experimental result. And if we just directly deploy what we learned offline, okay, because of sim real gap, it won't work. And we can manually tune for a specific task, but it's not generalizable. And proposed method does nice generalization and robust. Okay, so we extended this approach to apply how this works for the challenging work of screwing. And so brought to the screw. And this part, it was just done by robot. So successfully conducted this type of operation. And another work I would like to briefly introduce is contact-aware model-based learning from visual demonstration for robot manipulation via differential physics-based simulation and rendering. And we try to do something what Jitendra was doing. So there are quite a few demonstration videos available. So the natural question is how we can let robot do the same thing. So the Xinhao asked the three questions. What is the movement of the object? How should I contact the object? And how I can finally execute what we learned? So to the first question, essentially, it's a rendering problem. So he applied a self-supervised approach for pose estimation and shape reconstruction by differential rendering. And for the second part, essentially, he came up with some hierarchical manipulation scheme for contact-aware manipulation policy. Okay, so the low level, it does both the contact point localization and contact force optimization. And at high level, the two things are nicely orchestrated to make it work. Now, but this part is computationally intensive. So for implementation, he essentially did imitation learning from the generated plans from the second box. And the result was something like, okay, so on the left, it's the rendering part, and then in the middle, it shows some task which is learned from the scheme. And finally, it was implemented, like shown in the right. Okay, so it's result looks like very similar to what Jitendra was showing, but I think it started from the human demonstration data. Okay, so I think that Xinhao already did poster in the morning, and Shuran will be doing poster later. So if you come to his poster and if you ask him questions, discuss, I appreciate. Thank you very much.
Thank you, Tommy. Are there any questions? Maybe a question from my side, if I may. In industrial applications versus these sort of more home applications of cleaning the kitchen, is there a big difference in the kinds of problems that we care about, or is it fundamentally the same, deformable materials, etc.?
Which one?
Industrial. So you showed the assembly line of the kitchen appliances, for example.
I think it can be applied to other problems also. It's not, it happens to have a nice industrial robot with, we nicely coordinate our activity with FANUC. So we have lots of yellow robots in the lab, and that's how our test platform. Okay.
Perfect. Thank you very much, Tommy. Up next, we have Shuran Song from Stanford.
Okay, hello everyone, good afternoon. Really excited to be here and give you guys a quick update about our lab and what we are doing now. And I think the most important update is that we are here now. And over the summer, we successfully moved the whole lab across the continent from New York to Bay Area. And we are so glad that we are finally settled and sitting in this beautiful Parker building. And if you ever get a chance, please come by and say hi. So, what we are working on now. Okay, so earlier this year, we published this work called Diffusion Policy. So here is just a quick examples of all the, like a variety of different tasks that is trained using the same framework called Diffusion Policy. And then it's actually directly trained from human demonstration that the policy is inferring actions from images. So what is diffusion policy, right? So I think you guys probably know diffusion models for image generation, and here we're actually using a very similar idea, but instead of try to generate images from text conditions or text inputs, we're trying to generate robot behaviors, or in another word, robot actions, conditions on the visual observations of the environment. Right? So here we can actually train this generated model from a collection of human demonstration data. And what makes this diffusion policy or this formulation special is really this kind of iterative denoising process. And it turned out to be actually a really excellent way to help us to precisely model those complex multimodal distributions appeared in a lot of human demonstration data. And that is actually also something a lot of prior work actually struggled with. So in addition to the ability to model action multimodality, diffusion policy also actually has other advantages, like it's able to scale well with action dimension and also more stable to train. So today I'm not going to get into details of these properties, but I think all these properties are actually what make diffusion policy a very practical framework for learning almost any robot behaviors. So what's that mean to you maybe is that you can basically think about diffusion policy as a drop-in replacement for any other like policy representations that you're probably currently training right now, and you're very likely to observe some consistent performance boost just by doing these simple changes in your framework. So for example, this is actually what our friends in TRI is able to achieve by just applying this simple framework of diffusion policy to 100 of different tasks. And they're actually able to do something like pretty crazy, like flipping a pancakes, just with these very simple frameworks. So that probably means that you should try it out on your tasks and applications as well. So to make it easy to use, we actually released a Colab tutorial so that provide you the minimal code base so that you can easily get started with just like 1,000 lines of code. But before you try, I do want to mention a few limitations about diffusion policy. Right? So first is about data collection. Right? So in order to train an effective policy, it does rely on very high quality human demonstration data. Right? So for example, this mark flipping task actually can only collected by one of our experts in-house, like this Shuran actually from TRI, and that's not very scalable. And another thing about diffusion policy is that at least its current formulation only handles a single task. Right? It means that if you actually need to train different policy to handle different tasks, and this actually cannot be shared across different task skills. And in our lab, we actually work on a number of extensions, try to address the limitations of diffusion policy. And then today, I probably only have time to talk about, like, give you a quick teaser about one of them. So this project is called Scaling Up and Distill Down. And then in order to address this data problem, we try to scale up the data collection in simulation by using large language models. Right? So for example, given any task description, an unseen task, we'll use large language model to break down the task into subtasks and call the sampling-based utility functions to generate low-level actions. And then we also use LLM to generate a reward function to verify each of the subtasks' success using the simulation state. So by the end of that process, what we have is a very large multi-task data set with dense language label. But of course, that is actually relying on the simulation state. So therefore, in the second part of this project, we actually need to distill down all this robot experience into a lightweight visual motor policy that we can directly deploy it on the robot. And then, particularly in this stage, we're actually able to extend diffusion policy by considering multitask scenarios using language conditions. So I think today in the afternoon, Hui, the first author, will actually give you a poster presentation about this work. So feel free to drop by and ask more questions about the details. So to quickly summarize, I think what the project of diffusion policy really kind of convinced me is that we are maybe at the stage that if we are able to collect enough high-quality training data for robots, then we can actually train an effective policy for the robot to work for that one task. Right? So this sentence actually also precisely or exactly describes the limitations of this framework. And then that is actually what we are currently working on, trying to address, basically thinking about what are the scalable ways to collect training data, and also how to make our policy more flexible to handle multiple tasks and also reusable for new skills or scenarios. And I know that there are probably many different approaches to address those problems, and I'm happy to hear your thoughts and discuss about them. Thank you.
Any questions?
It's a very nice talk, thank you. I wonder, Chelsea was actually talking about doing everything in the real world, right? And you seem to be promoting the sim to real approach. I wonder what question you would like to ask Chelsea to convince her to try the sim approach.
Actually, that's a very good question. Actually, I'm not sure which one is better. I also find it very hard to argue like one is over the other. So today, actually, in one of the overview slides, I have two works that's actually both are kind of extending or scaling up the data. And one is actually the simulation work, and the other is actually trying to scale up the real-world data collection. And I think both of them has its own advantage and disadvantage. It's really hard to argue against. And maybe we should just push forward for both ends. Yeah.
Excellent, thank you, Shuran. I think the researcher answer is more research is needed. Up next, we have Steve McGuire from UC Santa Cruz.
Good afternoon. My name is Steve McGuire with UC Santa Cruz, and I run the Human-Aware Robotic Exploration Group there. So today we're going to be talking about leveraging robot sensors for doing ecological assessment in collaboration with with a collaborator in the Environmental Studies Department at UCSC. So ecologists perform their art with detailed, frequent measurements of trees, bushes, shrubs, and whatnot that typically consist of many individuals using basic tools and non-invasive methods. The center picture here is part of the army of undergraduates that are decked out in Tyvek suits with clipboards and measuring tapes, measuring trees. This entire process is labor intensive, it's time intensive, which means that we can only assess ecological properties every so often because of the resources that are required to do these kind of surveys. So why do we care? These ecological measurements give us the raw data for tracking a changing environment in terms of human influences, weather patterns, you name it. We can also observe the efforts of management decisions. For example, do we do a managed burn? Do we let it grow? How do we know unless we gather the data? It also lets us develop new management strategies that might include other novel land management decisions involving water or other land uses. So what kind of solution can we do? Well, this is Barks. We're going to add some robots, with the goal being that we're not going to replace the field scouts that the ecologists would deploy, but rather augment them. The role of the robots, then, is perhaps we can put the robots to measure things or go places that the people can't go, and preserve the people who are skilled experts for the places the robots can't go. We use robots that give us the opportunity for precision localization, better sensing, and even the potential for autonomy. The part of the challenges for ecological monitoring now is that we're talking about areas on the square kilometer class that robots, this is not just measuring a backyard patio. The terrain is often rough and rugged. Given the canopy of the trees, we will often have GPS denial, and we have many uneven obstacles. The operators that we would like to have are non-roboticists, ideally those field scouts that can drive the robot and direct the operation via teleoperation or other command sequence. And so this photo shows one of our current experiments to gather pilot data with a unitree quad in our research area on campus, which is convenient because it's a 25-minute walk directly north of our engineering buildings. That's been indexed and characterized for the last decade by my environmental sciences collaborator. That's a 6-hectare plot, roughly 200 meters by 300 meters, surveyed, that has a topographic map attached to it that we can walk to in an afternoon, open access, and gives us a ready test bed to demonstrate the effectiveness of some of our techniques. The particular goals we want to incorporate are 3 specific measurements, including diameter at breast height, tree species estimation, and tree decomposition estimation. So the DBH, or the diameter at breast height, is literally taking a measuring tape around a tree, approximating it as a cylinder using a tape measure, and recording the number, where you record the location and measurement. And if you see the plot on the right here, that's the location and size of every redwood tree in that plot. They get tagged with a little aluminum tag, and that's that. So this is an area that would be ripe for any kind of LiDAR/multimodal data reconstruction to not only recover the diameter, but other volumetric information about the trees to better understand their growth and better understand trees for which a cylinder is really a rather poor fit. The tree species identification may seem really obvious as to why we might want to do that. I learned that the real value is not necessarily what's alive, but what's dead, so that we can characterize deadfall characteristics for wildfire impact estimation. That ties into decomposition analysis of what's dead and can we categorize it into 1, 10, or 100-hour fuel sources. This is a picture, you can see it in sort of the left one, where it's a Felis schwinitzi fungus, which is this kind of brown fungus thing, and it kills trees and leaves standing deadwood, ripe for wildfire problems. As a big picture, we're interested in developing robotic ecology assistants that work with our skilled field scouts to increase the area and the tempo of the assessments so that at the end of the day, we get better, more accurate, more consistent data that the science community can make use of to really help us better understand this changing world. And I just want to take a second to thank my collaborators, Professor Gilbert and Professor Josephson, as well as my lab and my funding sources. Thank you very much.
Thank you, Steve. Any questions from the audience? And maybe Tia, you can come sit up for the sponsors. Tony. So this was interesting because it's clearly very much out in the wild, literally. Anything interesting that you learned in terms of the robots and how they perform when you put them in these real outdoors environments?
So one of the big reasons to use the quadrobot was really the terrainability aspects that we learned from, as a lesson learned from the subterranean challenge, that wheeled robots just don't cut it. And even unless you have something the size of a tank that can really just roll over and roll through, having more advanced forms of locomotion really open up a whole new world of possibilities of where we can apply robots and what other collaborations we might find within our own backyards.
Perfect. Thank you very much, Steve. So that's the end of our faculty session. Up next, we will have some brief sponsors and then the students. And I'd like to ask all of the students that are up in the second spotlight session that you please start lining up. Just so that we efficiently get to our afternoon coffee, which I think we're all desperate for. But first we get to hear from our sponsors, and then we'll get to the students.